So let's take what we learned about change of variables and apply it now to double integrals. So if I'm looking at double integrals over R and I want to do a change of variables, I want to switch to U and V, my region is going to change. Now it's going to correspond to S, which is the corresponding region in the UV plane. And now you're going to plug in for X, you're going to plug in the equation in terms of U and V, and the same thing for Y. And then you're going to multiply by your extra factor. It's the absolute value of the determinant of the absolute value of the Jacobian, du dv. So let's revisit this example we kind of looked at in our last video, but now we're going to apply it to an integral. Let R be the region bounded by the lines x minus 2y equals 0, x minus 2y equals -4, x plus y equals 4, and x plus y equals 1. Evaluate the double integral over R of 3 of xy dA. So if you looked back at our last video, you would see that these 4 equations here were the equations that we had before. And so in our last video, we found that we should use the change of variables. What did we have? We had x was 1/3 2u plus v, and y was 1/3 u minus v. So we're going to need the Jacobian. So let's start there. Let's find the Jacobian, partial of xy with respect to uv, right? The partial of x with respect to u, partial of x with respect to v, the partial of y with respect to u, the partial of y with respect to v. So here, the partial of x with respect to u would be 2/3. X with respect to v would be 1/3, 1/3, and -1/3. So then you multiply diagonal minus the off diagonal, so you get -2/9 minus 1/9, or -3/9, which is the same thing as -1/3. Now we're ready to start changing our variables and our integral. A double integral over R. So it's the double integral over our region S now. 3. Plug in for x, it's 1/3 2u plus v. Plug in for y, it's 1/3 u minus v. And then you want to take the absolute value of our Jacobian dv du. So now remember how we described the region S in our last video. U went from 1 to 4. V went from -4 to 0. And we're going to get, so this 3 and this 3 cancel. We get a 1/3 2u plus v, u minus v, the absolute value of -1/3, dv du. So here we're getting 1/9 from 1 to 4, negative 4 to 0. And if I FOIL these two out, if I multiply that out, you should get 2u squared minus uv minus v squared. So you're going to get a 1/9, the integral from 1 to 4, integrate with respect to v first, 2u squared v minus uv squared over 2 minus v cubed over 3 from negative 4 to 0. So remember, you plug in top number. So if I plug in 0, they'd all be 0 minus, if I plug in a negative 4, it'd be negative 8u squared minus 8u plus 64 over 3. So we're getting a 1/9 8u squared plus 8u minus 64 over 3. So then just integrate with respect to u now. We're down to a single integral. This is 8u cubed over 3 plus 4u squared minus 64 over 3u from 1 to 4. If you plug in 4, subtract 1, you should get, in the end, 164 over 9 for the answer here. So again, what this change of variables did was take my not so nicely shaped region, and it turned it into a rectangle, which is really a easy region to integrate over. Rectangles are one of the best regions you can have. So that's why we did this change of variables here.